So let's try to get started again. Let's see. I found out during the break that unfortunately I hit the start streaming button but forgot to hit the start recording button. I talked to some of you in chat during the break, but it seems very likely that at this point I should be saying hi YouTube, because it's likely that I will not be able to recover the first hour of this stream. Sorry for that. Please take a careful look at the slides, study them well, and if you have any questions about them, feel free to ask them via the Brightspace forums, and I'll be happy to take a look. Most important things we discussed was a refresher of big O complexity notation. I introduced the topic by taking you through a bit of a retrospective on the other algorithmic courses you've taken so far. And we were working on creating a decider for the language a to the power m, b to the power n, where n is larger than m, meaning a number of a's followed by a larger or equal number of b's. We also discussed some questions about the course at the start. The main question I'd like to reiterate here was a question about the exams, and all I can say is that I know you got an email that says that 4 days in advance you will hear from us what we're going to do. We hope to tell you sooner, but I don't know when. All I can say is as soon as possible. Okay. With all that said and done, let's take a look at decider number 3 for this language. So we already saw one that does it in quadratic time. We already saw one that does it in n log n time. Now let's see if we can still do better. And some people had some good ideas during the break that we discussed a little bit in chat. So one of the ideas, and let me scroll up here so that they can give the proper attribution. So Jonathan asked, could it be not used a RAM machine, or is that cheating a bit? And someone else said, well, how about we use a multi-tape machine, right? So SH asked that, and also Hightech said, how about we just write all the A's to a second tape and step through it together with the B's? Well, that is a bit cheating, right? I mean, we're using extra hardware, but it's still a Turing machine, and as it turns out, I'm cheating too. So indeed, scan the A's on the input tape until you reach a B, and then copy those onto a work tape while you're doing that. And now, as we scan the B, every time I find one, I remove an A from the work tape. If I now have any A's left, that means there were more A's than B's, I reject, otherwise I accept. So here's an alternative solution. It does use work tapes, but what is the time complexity of, of this one? Well, we'll skip asking it in feedback fruits. I already told you we were looking for something better. And I hope you can see that this is a linear time machine, right? It just scans the tape once. For the first bit with all the A's, it does some copying. For the second bit, it does some removing. But all of these are constant time operations on my work tape. I just need to keep track of my pointer, moving it forwards first as I'm copying A's, and then moving it backwards as I'm removing them. No extra time involved there at all. And then if there's any A's left at the end, well, that's simply checking, am I pointing at an A or not? I can reject, otherwise I accept. A linear time solution. But it does require a work tape. Now, when we introduced the notion of complexity analysis all that time ago, one of the reasons we gave you was that it made a lot more sense to talk about big O because we could get rid of some of the dependencies on hardware that we normally had, right? We would say, well, it makes no sense to argue, is it n plus 8, or is it n plus 16, or is it n plus 32? Because it depends on the CPU, it depends on the compiler, it depends on a whole lot of stuff that we shouldn't care about. All we should care about is that it's n plus a constant, and therefore n is the bottleneck. But now, a change in hardware loses us a whole logarithmic term. We can go from n log n to n, or from x log x to log x. X log x to x. Right? That's quite an improvement, and it's just based on having a bit of different hardware. So, how do we do that, right? That seems to go against this notion of big O, which was meant to abstract all of that away. And now that we are at the final hurdle of this algorithmic track, the final challenges, we would like to discuss the problem instead of the algorithm, right? We would like to say whether this problem L that we are discussing, whether that's an easy or a hard problem. And now we have 3 different algorithms with 3 different runtimes. How on earth can we then say something about the underlying problem? So the question we ask is, okay, how do we define the complexity of a problem, preferably in such a way that hardware and software dependencies are not important, right? That the difference between an n log n and an n algorithm and the difference between a single tape and a multi-tape Turing machine all becomes irrelevant. Now that's quite tricky, but fortunately also doable. So let's talk about the complexity of problems. Complexity of problems. Let's start with a definition straight away. The complexity of a problem is the worst case complexity of a best algorithm for the problem when executed on a predetermined machine model. That's a lot of information there. Okay, worst case complexity. We know what that means. Okay, best algorithm. What's that? Well, an algorithm A is a best algorithm for X if every other algorithm takes at least the same amount of time. And notice that I'm saying for every n, right? So not after a certain point, as is used for case for big O, but just always. Now, that's slightly problematic because, how do I determine whether something is the best algorithm? Right? That requires me to think about any other algorithm for the problem. How can I ever determine all of the algorithms? And to add to that, this IDEAS also still says, so for complexity of a problem, when executed on a predetermined machine model. So the complexity of a problem would still depend on what machine model I use. A problem would be easier or harder on a single tape machine than it would be on a multi-tape machine. But it's just a problem, right? It shouldn't matter what kind of machine I run it on. The problem is still the same. So perhaps this definition, although it gets us closer, still isn't exactly what we want. Perhaps we can do better. Well, as it turns out, we can focus on the one-tape deterministic Turing machine. And in a moment, a couple of slides and a couple of minutes from now, we will be introducing a new first complexity class for a complexity of problems that is independent of the machine model and independent of the algorithm used. Well, we only care that it has that the algorithm meets certain requirements, but we don't care exactly what it is. And we will focus as our choice for machine on a one-tape deterministic Turing machine. Now you might think, okay, that sounds easy, Stefan, because we've already seen that k-tape deterministic Turing machines, even non-deterministic Turing machines, are all equivalent in terms of what they can do. And you're right. We have seen already that they are equivalent in terms of what they can do. But remember, now we're talking about how fast can they do it. And these are 2 very different questions. They can decide the same set of problems. But now the question is, how fast can they decide these problems? And this is where I'll show you a theorem. I'm not going to prove it. You don't need to know the proof for this one, though it can make a very stimulating read if you're looking for some night bedtime material. There is a nice theorem that says that for any k-tape Turing machine that requires t of n time to solve a problem, we can create an equivalent single tape machine that solves the problem with quadratic overhead, so in t squared of n time. So for example, if our k-tape machine requires on time, we can simulate that in on squared time on a single tape machine. So this is already where we see a first distinction, right? So k-tape machines are indeed a bit more powerful in terms of speed, not in terms of what problems they can solve, but they are a bit more powerful in how fast they can solve them. But a single tape Turing machine only requires quadratic overhead. And someone took that idea someone whose name you are familiar with, someone called Turing, together with someone called Church, and they formulated the strong Church-Turing thesis, which says that every physically realizable algorithmic process can be simulated on a one-tape deterministic Turing machine with polynomial overhead. So the previous is an example of that, right? A k-tape Turing machine we can do with quadratic overhead, polynomial overhead. But this thesis goes one step further, and it says that any machine, my desktop that I'm using right now to stream to you, my laptop that's in front of me here, this tablet that I have set up, my phone, any machine can be, or anything these machines can do, a single tape Turing machine can also do, with only polynomial overhead. So polynomial n to the power some constant, right? So it could be quadratic, could be cubic, could be n to the fourth, could be n to the 80th, but n to the power some constant. Now this is a thesis that we generally accept, but we cannot or have not proven. Because how would we prove this? It would again require us to think about every physically realizable algorithmic process that requires us to reason about machines that may not yet have been invented. But it's still generally accepted, with only quantum computing forming a possible exception here. But for quantum computing, the question is, do we consider that how do we consider that, right? It might not be deterministic, and therefore we might run into issues with our polynomial overhead. So quantum computing may form an exception to this rule, but at the moment we don't know, right? So this is another misconception. Yes, quantum computing allows us great things, but we don't yet know whether they are really fundamentally more powerful than Turing machines. So this says that polynomial overhead is all it takes to transform an algorithm written in Java to an algorithm for a Turing machine. Okay, what does that mean? Well, it means that we can now start defining some complexity classes. Consider, for example, the complexity class time t of n. Time t of n is a very broad thing. It says it's all of the languages that can be decided in OT of n time. So for example, time of log n is a thing, and it is all of the languages that can be decided by an O log n one-tape deterministic Turing machine. Now we saw our language L earlier. Which of these is that an element of? Is it an element of time log n, time n log n, time n squared? Let me open it in feedback fruits. There we go. And I'll give you a bit of time to give me an answer. And let's take a look. Okay, answer C is by far the most popular. Yes, so we indeed saw that we found an n log n algorithm that can work on a single tape Turing machine, as well as an n squared algorithm. So it belongs to C, but by extension then it also belongs to D, right? Because if something is O n log n, it's also O n squared. So C and D are both correct answers here. Okay, well done. Remember that the algorithm we saw that was linear time wasn't a single tape machine. And time, T of n, is still for single tape machines. So answer B, unfortunately, is not correct here. But again, that's a problem, right? And we didn't want that. We didn't want this hardware dependency, which is why we will start grouping some of these classes. And to start with, let's make a very broad distinction. Let's have polynomial time algorithms and exponential time algorithms. So polynomial time means it's O(n) to the power some constant, for some constant larger than 0. And there's another great notation that some people use for this. Personally, I find it less clear, but yeah, it says the same thing. And exponential time, in contrast, is 2 to the power n to the power some constant. And this is how we can also make 3 to the power n, right? By choosing the appropriate constant. So these are the two classes we have for now. Polynomial time on the one hand, exponential time on the other. And let's zoom in a little bit on polynomial time algorithms. And now we get to our first class from the ultimate challenge, P versus NP. We can define our class P. P is everything that can be decided in polynomial time. There's 3 ways here in which we can describe this. It's the set of all languages decidable in polynomial time. And this is our first example of a robust complexity class. It doesn't matter what kind of software I use, so long as I find a polynomial time algorithm, could be n squared, could be n log n, could be n, could be log n, I don't care. If it's polynomial time, it's in P. And it doesn't depend on hardware, so long as it's a deterministic model. Right? So if I use a single tape Turing machine, or even if I use my laptop, both are deterministic, and according to the strong Church-Turing thesis, which for now we accept, so to answer your question, Klaas Vaak, we accept it because, well, quite frankly, so far we found no counterexample. We have no way to prove it, but we have also not found any evidence against it. And so every model we have created so far, we can indeed show that with polynomial overhead, we can also do this on a single tape Turing machine. And so the class P is now robust. Whatever deterministic hardware I use, all I can do is add polynomial overhead. That's fine. It will still be in P. All right. I see some discussion going on about this K-tape and transforming it with quadratic overhead. I'll come back to that in the break, if that's okay. Our first class, P. All languages that can be decided in polynomial time. Well, you've seen problems in P already. Consider this one. Given a graph and a weight function, and 2 vertices, S and V, or S and T, is there a route of at most weight K from S to T? This is a problem that is in P. It is also a decision problem. The answer is either yes or no. And we can solve this one using, for example, Dijkstra. And that means that there is a polynomial time solution. The polynomial time, yeah, it was either v squared if you didn't use a priority queue, or if you did use one, it was e plus v log v, whatever. It was polynomial time. And that means that this problem, shortest path, is in P. Similarly, in algorithm design, you run into something like this. We have jobs with a processing time and a deadline. Can we schedule them so that at most k jobs are late? And using some greedy solution, we could show that this was indeed also doable in polynomial time. So problems in P, you've already seen plenty of. In fact, almost all of the problems you've seen have an equivalent decision variant, where the answer is just yes or no, that is in P. Namely, everything you've ever done that has a polynomial time algorithm is in P. So P contains quite a lot. And now we say that problems in P are easy or tractable, and we say that problems that are not in P are intractable or hard. Now, why is that? Why do we say that P is easy? Well, we say that because when we take a look at our systems, what is the impact of a system that becomes 10 times faster? Right? So if I have a machine that becomes 10 times as fast as the machine I'm using now, then for a linear algorithm, so for a linear problem I should say, we can solve an instance that's 10 times as large in the same amount of time. For something that is n squared or n cubed, I can solve something that's 3.16 or 2.15 times larger. But for something with exponential growth, so something that's not in P, we can only solve something that is 3 bigger. Not 3 times bigger, but 3 bigger. So imagine I have a graph with n vertices. Now I can solve a graph of n plus 3 vertices in the same time. And that's nothing on a graph of a couple of thousand vertices. So a machine that's 10 times as fast adds pretty much nothing for exponential time algorithms. For n factorial algorithms, it's even worse, right? For any n larger than 10, it's not going to make a difference at all. I'm not going to be able to solve the problem that's even 1 bigger with a machine that's 10 times as fast. So what does this mean? It means that for problems in P, technological process, a constant factor speed up, something becoming c times as fast, actually matters, because it allows us to solve problems that are c to the power 1 over k times as large in the same amount of time. Getting a factor 10 speed up allows us to solve problems that are 10 times as big for linear problems. And similarly, problems that are not in P, this technological progress doesn't really seem to matter, because the instances we can solve with our faster machines are only a constant bigger instead of a constant times bigger. So if our machines get 10 times as fast in a year's time, I can now solve a problem of size 18 instead of 17. Great, but that doesn't really help me. Furthermore, exponential time algorithms, the problems in NP, or sorry, the problems not in P, that's how I should say it for now, the problems not in P, we have exponential time algorithms, and these are often brute force solutions, right? They're not very elegant, not very nice. And I realize that sounds a bit weird maybe, but what I mean to say is that problems that are in P have a solution that really provides insight into the problem. Consider Dijkstra's algorithm, or PRIM for MSTs, which has a certain elegance, right? It's using properties of a graph to find the MST in the case of PRIM. And it's using properties of a graph to find the shortest route in the case of Dijkstra. They have some sort of beauty, some sort of elegance to them. Instead of simply dumbly just trying all the options, which is what brute force exponential time algorithms often boil down to. And we have some empirical evidence, again, nothing strong here, but so far, most of the polynomial time algorithms that we found actually have a very low value in the exponent, typically a k that is at most 4. So n squared, n cubed, sometimes you see n to the 4th, but bigger than that is very rare. And that's also something nice, right? Okay, polynomial could technically still be n to the power 500, which is arguably as bad as 2 to the power n, but n to the power 500 we never really see. Usually it's small exponents and therefore very, reasonable times. So these are some reasons as to why we say, well, P is a class of easy problems. Okay, easy problems in P. Our challenge is going to be about P versus NP. So perhaps it's time to take a look at the other half of this equation. We now know what P is, problems that are decidable in polynomial time. What about NP? NP has just one addition. It is problems that can be decided in polynomial time by a non-deterministic Turing machine. So P deterministic Turing machine, NP, non-deterministic Turing machine. A common misconception is that NP is for non-polynomial. This is absolutely false. NP is the abbreviation for non-deterministic polynomial. It's still polynomial time. The only difference is that I've gone from a deterministic machine to a non-deterministic machine. And this makes all the difference in the world. Because as it turns out, non-deterministic Turing machines can use time in an altogether different way. And my question to you is, how can they use it? So if I have a non-deterministic Turing machine that can solve a problem in t of n time, O(t) of n time, then a one-tape deterministic Turing machine can simulate this in one of these options. I wonder if you can tell me which one. All right, let's take a look. Answer C is the most popular answer. It has some sort of exponential overhead. Yes, you're right. How does this work? Well, you can think of our non-deterministic machine as exploring a bunch of different paths. Exactly, as Pavon points out, we need to try all the different options that our deterministic machine can afterwards simulate, right? It can try all the different options our non-deterministic machine could normally take. So such a large tree, where we check every option with a lot of backtracking, requires indeed exponential time to check all of the different paths, all of the different options that the non-deterministic machine could take. Yes, thank you, Pavon. Nice answer. As for Jonathan, you're asking, what about the other way around, right? So if I have something that can be done in exponential time on a deterministic Turing machine, am I guaranteed to be able to do it in polynomial time on a non-deterministic Turing machine? The answer is no. This is not necessarily true. So the class exp, which contains exponential or problems that have an exponential algorithm, is not necessarily the same as the class NP. P is a function, Francis, or from Francisco. I'm not sure where to stop pronouncing your name, but yeah. So P is a function, some polynomial function. Jonathan, you're asking, you saying not necessarily. Is this proven? No. So also the question, is NP the same as exp? As far as I know, is an open question, but that's not something we usually discuss, so I'd have to double check. But my gut feeling is to say no. Would you say quantum computing comes in here, where quantum computers can simulate NDTMs, where normal computers can only essentially do deterministic machines? Very nice question, SC Arcade. So quantum computing, we do not yet know whether they can solve all problems in NP efficiently. So no, quantum computers we do not yet know how they can efficiently simulate an arbitrary non-deterministic Turing machine. So this is also still an open question. Okay, so indeed going from non-deterministic Turing machine to deterministic Turing machine requires exponential overhead. But if I tell you, okay, take your non-deterministic Turing machine, I tell you that this path, and I point it out to you, this path is an accepting path. Then you could check that claim very easily. You can check that in polynomial time. Why? Well, the non-deterministic Turing machine runs in polynomial time. Otherwise, it's not a part of NP. So that means the path can be at most a polynomial length in terms of the input. And now you only need to check this one path. And checking that one path requires polynomial time. No more, no less. And that's great. So checking one path, we can do in deterministic polynomial time. Which means that for these problems, if I give you a certificate, a path through the non-deterministic Turing machine, in terms of problems, if I give you a solution, you can check my solution in deterministic polynomial time. And so our class NP is a little bit more interesting, because the problems in NP minus P, well, they can be solved on a non-deterministic machine in polynomial time, which means that there's exponential time required to do it in a deterministic machine. But verifying a solution can be done in polynomial time. If you show me which path to check, I can check just that one path easily. So why do I talk then on my previous slide suddenly about NP minus P? Well, I do this because P is a subset of NP. Everything we can decide in polynomial time is a subset of everything we can decide in non-deterministic polynomial time. Why is that? I'm giving you some options to choose from here. Okay, let's take a look. Answer A is very popular. Answer B has some votes. Answer C has a fifth of you convinced and a couple for no clue. All right, so let's start with answer A. Every DTM is a special form of an NDTM. Well, that's true, right? Every deterministic Turing machine is just a non-deterministic Turing machine as well. Which means that it's based on this, if we say every problem that can be solved using a deterministic Turing machine in polynomial time, every problem that can be solved using a non-deterministic Turing machine in polynomial time, yeah, that includes all of these problems as well, because every machine we have here is also a non-deterministic Turing machine. Every deterministic one is also a non-deterministic Turing machine. So answer A is indeed a correct justification of the claim that P is a subset of NP. Now answer B is also correct. Right? Remember that the alternative definition for NP we saw is that verifying a solution is easy. Well, we can easily verify a solution to a problem in P. What do? I just find the solution and I check whether it's the same. Right? Finding the solution I can do in polynomial time. That's why the problem is in P. So verifying a solution, well, if you give me one, I'll just run my algorithm to find this solution and compare whatever you're telling me with the solution I found. So answer B is also correct. Answer C, however, is not. This says because we can transform a DTM to a non-deterministic Turing machine with exponential overhead. But okay, first of all, sure, I guess we could do this. But we don't have to, because a DTM is already an NDTM without doing anything. And if I were to add exponential overhead, that would not be a good thing, because as soon as I add exponential overhead, this NDTM that I've constructed will no longer run in polynomial time and will therefore not be a proof that this problem is in NP, because it still requires non-deterministic polynomial time, not exponential. So P is indeed a subset of NP, and both answer A and B are correct justifications of this fact. All right. Let me take a look here. Yes, let's do a little bit more before I send you off into a break again. So that means that now we know the two parts that form this thing that last week I introduced as the ultimate challenge in computer science. The class P, everything that can be decided in polynomial time, and the class NP, everything that can be verified in polynomial time. And the question we still have in computer science is, are these things the same, yes or no? And that's a very interesting question, even though you might now be asking, okay, but who cares, man? As long as we have some problems we can solve, that's great. But well, the problem is that there are many problems that we believe to be in NP minus P. Problems that we have no polynomial time algorithm for, but whose solutions we could easily check. And problems like this include constraint satisfaction, for example, scheduling, routing, packing and stacking problems, chip and system design problems, right? How do we fit as many gates onto a small circuit as possible? All this kind of stuff is NP hard problems. In fact, just creating a truth table is something that requires exponential work. Right? If I gave you a formula in reasoning and logic and I asked you, can this thing be true? What would you do? You would create a truth table. You would try all the options. But if I tell you, well, it's true for P equals 0, Q equals 1, R equals 0, you only need to determine one row of your truth table. Verifying it can be true is easy. If I give you the solution, you can very easily check. Figuring out whether this thing can be true required you to do exponential work, create a truth table. So this class of problems, NP minus P, contains many, many real-world problems. Now someone is already skipping ahead a little bit and is asking, is NP hard and NP minus P the same? No, it is not. And unfortunately, the answer from our moderator is not entirely correct either. But we'll get to NP hard later. NP hard and NP intersect, but it's not true that all of NP is in NP hard. To correct 6108's answer there. Okay, so NP minus P contains a lot of interesting problems. Problems that we have no polynomial time algorithm for, but that we can easily verify. Now, and if that is not enough of a reason to care, of course, remember that this is also one of the Millennium problems, and that solving it one way or the other, right, showing either that P equals NP or that P does not equal NP will get you $1 million. So if you don't do it for the science and you are interested in the money, this could be a good reason to consider doing so. Now, many of these slides today are based on one of the slides of one of my colleagues, Kees Witteveen, who's been teaching complexity theory for many, many years at our university, and whose retirement party I attended 2 years ago, but, well, he's still back this year to teach. He always says that he gave it a go once, tried to write a proof that P equals NP, focusing in on one very specific problem, and after spending many weeks working on this and handing it in, he got back a very polite email saying that, well, there was a mistake on line blah of his proof, and that they encouraged him to fix it. Of course, well, I say of course, unfortunately, he was unable to, right? But if you want to, well, people are still submitting proofs for this idea one way or the other. I wouldn't say every day, but many times a year. I encourage you to take a look at it. Pick a problem you like and try and give it a go. I say pick a problem you like, and we'll talk about that a little bit more towards the end of today. So if nothing else, then there's still a lot of money to be earned. Great, another extrinsic motivation. Now, let's take a look at two problems in NP minus P. Problems that we believe to be hard. Because we believe there is no polynomial time algorithm for it unless P equals NP. So, vertex cover is a first famous example for that. We have some graph with vertices and edges and an integer k. I am looking for a subset of vertices, at most k of these vertices, such that all of the edges are covered, meaning one of the endpoints of the edge is in my vertex cover V prime. Can anyone tell me a real-world application of this problem? Silence so far. If not, then I will give you one, but I was sort of hoping you might be able to come up with some. You want every city to be connected to at least one street? Okay, but it's sort of the other way around in vertex cover. So we want every street to be connected to at least one city, I suppose, right? So vertex cover, the name is a bit odd, but we're looking for a cover of vertices that cover all the edges. Ah, Frostbite, you have one of our classic examples, but it's a very good example, and the one I was also going to use in a drawing that I'm now going to make. Imagine you have some corridors that you want to keep. Let me just move my keyboard out of the way here. That you want to keep watch on. And imagine, for example, that this, I'm just drawing some stuff at random now, but it should do, that these are some corridors in your building, and the vertices indicate intersections of these corridors. Now you want to know, with at most 2 cameras, can I cover all the corridors? Well, in this case, we can try and see that, well, 2 is probably going to be problematic. One vertex cover here would, for example, be this one, which covers these edges. Then I still need one of these, so let's pick this one to cover this edge. I still need to cover these 2. I can do that by picking this one. And finally, I need to cover this one, so let's pick this one. So here I found a vertex cover of size 4. And now this thing is going to show us a poker ad, which I'd rather not do on stream, because the licensing for this thing is horrible. I tried to buy it, but the only subscription available was a lifelong one for €100, and I'd rather not. There we go. We're back from the poker ad. So this is an example of vertex cover, right? We have corridors that we want to cover by placing cameras in our intersections, in our vertices, strategically. Yes. Are there questions about this problem of vertex cover? While I answer tumble checks. So to clarify, problems we currently consider to be elements of NP minus P might actually be in P. We can't definitely prove whether they are in P or not. And you are absolutely right. It fully depends on whether P equals NP. If P equals NP, then NP minus P is empty, and therefore this problem that we now believe, so for example, vertex cover, would also be in P. But if NP does not equal P, then we believe vertex cover to be a problem that is not in P. And we'll talk a little bit more about that after our break. Are there more questions about vertex cover or about NP minus P or anything like that? As I get my keyboard back. You're very welcome. Let me transition this away again. Can we prove that if P does not equal NP, that this problem is in NP and not in P? Remember that being in NP is not enough, right? Because P is a subset of NP, so we really need to show them that it's in NP minus P. Yes, we can. So this is a problem that is what we call NP complete. And we will be talking more about that class of problems today, but also next week, and about the relations to P and equaling NP. All right. If there's no other questions for now, then I suggest we have another small break. I will stick around in chat again, answer any questions you have, and I will see you 15 minutes from now. right, so let's try to get started again. So before the break, I introduced the first problem, vertex cover, that currently we believe to be in NP minus P. But that requires me to show you at least one more thing, right? It requires me to show you that this problem can indeed be verified in polynomial time, or that a non-deterministic Turing machine could solve it in polynomial time. Well, how do we do that? Well, given a solution, right, given a set of vertices, I can check, are there at most k of these vertices? And I can check, do they cover all the edges? What do? Well, I loop over all the edges, and for each of its endpoints, I check whether they are part of this solution you gave me. This I can clearly do in polynomial time, right? It's linear in the edges, multiplied by however long it takes to check if an endpoint is in your solution. If it's a set, then it takes constant time. If it's a list, it takes linear, whatever, right? Some amount of polynomial time to check that. Polynomial times polynomial is still polynomial. So indeed, verifying the solution can be done, or verifying a solution can be done in polynomial time. So this problem is in NP. Why then do we believe it to be in NP minus P? Well, because we have not yet, I say yet, we have not found an algorithm that can solve this problem in polynomial time. We can verify a solution, but not find the answer. And that's why currently we believe this problem to be in NP minus P. Let's take a look at one more. This is the problem of clique. Again, given a graph and a positive integer. Again, give me a subset of at most size k. This should be of at least size k. I should fix that. Let me make a note. So give me a subset of at least size k, such that all of the vertices in it are directly connected with an edge. Again, I can draw this for you. So, given a graph, let me actually do this in white again so that I can use green to indicate a clique if we have one. A graph with some edges. Something like this. I could ask for k equals 4. Is there a group of at least 4 nodes that are all connected to one another? And the answer is yes, there is. Here we go. Again, given a solution, given a set of nodes, I can check, are these at least k nodes? And is it true that all of these nodes are connected to each other? So, given a solution, I can easily verify it. Every time I say easy, you should read polynomial time, or you should hear polynomial time, right? So I can verify the solution in polynomial time. I cannot, however, or at least not yet, efficiently, easily find a solution. So at the moment, we have no polynomial time algorithm to solve this problem, only to verify solutions. So this is another example of a problem that is in NP. There's no doubt about that. But at the moment, we believe not to be in P. It's in NP, but at the moment, we believe it's not in P. Okay, let me hide the tablet again and focus back on the slides in full. Examples of this problem I've already shown you. Remember the very start of our lecture when I showed you some examples, right? We might be looking for a group of people that are not adhering to our social distancing laws. We can find the largest group of people by finding a clique of at least size k, right? We can find out, is there a group of people of at least 10 people that came together? But there's a whole bunch more in biology and all kinds of other applications of the clique problem. All right. Now this was meant to be where we had to break, so we're a couple minutes behind schedule, because now I wanted to take a little bit of time to get to today's intermezzo, just like in reasoning and logic. And I wanted to talk a little bit about P versus NP outside of computer science. So first of all, I have a nice story for you here, and my question is, what is this story about? Now, if you think you know the answer, please don't post it in chat yet. Give everyone a chance to take a look, and after the timer has run out, feel free to post your answer if you have one. So the question is, what is this story about? All right, so feel free to let me know if you have an idea what this might be about. Context. Okay, that's even more meta than I thought it would be. Ah, yes, Linson, excellent. Yes, it's about flying a kite. Also, Lich, yes, kites. Cycling, maybe. Although, better to run than to walk. I'm not sure how that would fit in with cycling. Rock climbing, great. Yeah, I guess many of these things also still apply. The last one is a bit morbid then, but yeah. But flying a kite, or kite flying, is indeed the answer we had in mind here. And this, to me, is a nice example of a puzzle, right? And it's also a nice example of something that you could argue is in NP, right? Now that you have the solution, now that I've shown it to you, you can easily verify that, yeah, this story is indeed about kite flying. But when I only gave you the story, it was a little bit harder to come up with this answer. And this notion of there being a difference between finding a solution and verifying a solution can be generalized a little bit to other things. For example, in mathematics, is it really harder to verify a proof than the other way around? Is it harder to construct one than to verify one? This should be the other way around. Right? Constructing a proof is something we generally think is very difficult, but verifying a proof is supposedly much easier because all we need to do is just follow the steps. And so maybe it's true that verifying a proof is in P and constructing a proof would be in NP. But if so, that would mean that P equals NP would mean that it's just as easy for you to come up with a proof as us to check one. All of us would be the next Gauss. We would be able to come up with very nice and new fancy proofs. In physics, right, are there processes in nature that can actually solve these problems we think are hard? Are sunflowers, are bubbles, is gravity a more powerful computer than our computer is? And in art, is there a difference between recognizing art and creating it? Now, any artist will tell you that yes, there is. And well, I tend to agree. I am no artist, definitely not. And those of you who have ever tried to see me try and draw something on a blackboard will testify to this. But I can appreciate art. But if P equals NP, then maybe they are the same, right? Checking whether something is nice and whether something is artful might be just as hard as constructing something that's artful. Now, there is a great video. It's called The Complexity Zoo. and I'll link it in chat later as well, and of course the slides will be available on YouTube, that I really, really recommend you watch. It is a beautiful video that explains everything that makes P versus NP such an intriguing puzzle to work with. And they also talk a little bit about the further ramifications of this question beyond just computer science. So if nothing else, check this out. All right, so far for today's Intermezzo, let's talk about more complexity classes. So if you take complexity theory, which of course you are not, right? For you it's only part of Automata. We would be talking about a whole bunch more of these classes. We've now talked about P and NP, and I've told you that P is a subset of NP, but there's so much more. Well, you've seen decidable and you've seen recognizable, and this is of course just a subset of that. But there is so much more than that, so many more distinctions we could make. Unfortunately, we are not going to do that. We are going to zoom in on P and NP a little bit more though. And what I'd first like to do is show relations between problems. Let's see if we can, if I know something about one problem, learn something about another. For example, how could I show that a problem A is no harder than a problem B? Well, hang on. Didn't we do that last week when we talked about reductions? Well, yes, we did. And we can use the same here. If we can solve a problem A by using an algorithm for problem B, well, then A can be no harder than B. Because if I solve B, I also solved A. And this is the idea of reductions. Now, in complexity, instead of computability, we talk specifically about car productions. And car productions are a special form of reductions. What do? They take an instance of a problem A and they transform it into an instance of a problem B, such that if it is a yes instance of A, it becomes a yes instance of B. So if the answer was yes here, after the transformation, the answer will also be yes here. And the other crucial property is that it's polynomial time. We'll take a look at this mapping in a bit more detail in a moment. Now then we have some notation that you've seen before. We will still use the smaller or equal to symbol, which is potentially confusing because we also use it for reductions in computability, but yeah, I'm afraid that's the way it is. We might add a small k if it's really unclear and we really want to specify that we're talking about car productions, k for u like this. But what does it mean? It means that A is not harder than B. It means that A is car producible to B. Example, or rather a bit more visual of an explanation. Consider a problem A. The problem A has yes instances, which are indicated by the box here, right? All the words that are in the language in forms of graphs in vertex cover, all of the graphs that have a vertex cover of a certain size k. And outside of that, all the no instances, all the words that are not in the language. For example, a graph with a vertex cover, or with the smallest vertex cover of 6, and we're asking, is there one of size 5? Now, what should this car production do when mapping A to B? It should make sure that it maps yes instances to yes instances, and no instances to no instances. If we want to be a little bit more formal about that, then for all x in sigma star, if x is an element of A, f of x should be an element of B, yes instance becomes yes instance. And for all x that are not in A, the f of x should not be in B. So a no instance remains a no instance. And of course, the other criterion was that a car production should be polynomial time computable. Questions about this definition of a car production? We'll look at its properties in a moment, but is the idea at least clear? So we look at some function that takes a problem of type A, transforms it into a problem of type B, without changing the answer, right? If the answer was yes here, it remains yes. If it was no, then it remains no. So which is stronger, asks Pavon, A or B? I think with stronger you mean harder, maybe? So if we have a reduction from A to B, then A is not harder than B. But we'll see exact properties of this in a second, when we talk about the relation to the classes P and NP. Does that make sense, Pavon? What I just said about A not being harder than B? Is that what you meant? Does one include the other? So you mean is A a subset of B? Because that doesn't have to be the case. So we could, for example, have vertex cover as our problem A and clique as our problem B. And we could map vertex cover instances to clique instances to show that the vertex cover problem is not harder than the clique problem. I see an OK, so I guess something I said in there made sense. Good. All right. Does it need to be bijective, asks Scannerface. It's a good question, but as you can... so does it need to be bijective? Well, yes, in the sense that if it is a yes instance of B, it must also have been a yes instance in A. But it doesn't have to be bijective in the sense... Well, so no is my answer. Because, for example, if we take a look at the visual representation here, these problems outside of this darker blue box, right? You can see my mouse. These problems are not mapped to. And also these little things are not mapped to. And that's fine, right? So we only map into this little box, but every yes instance remains a yes instance, no remains no. It's just that these are not mapped to, but that's not a problem. So no, it does not have to be bijective. So we could use B to solve A valor, but not the other way around. Unless I find a reduction from B to A. But if I have a reduction from A to B, that only means that I can solve problems from A by using an algorithm for B. I'll show you how exactly in a moment. All right. Here are some properties of these car productions. And they're very nice properties that we tend to use a lot. If x is reducible to y, right? If x is car producible to y, then if y is in P, x must also be in P, meaning P is downwards closed. We'll see why that's true in a moment. If y is in NP, x must also be in NP, meaning NP is also what we call downwards closed, right? X is smaller or equal to y, so if y is in NP and x is smaller, easier, it's not an entirely correct explanation, it just means x is no harder than, but then x must also be in NP. And if x is NP hard, so if x is NP hard, then y must also be NP hard. Now NP hard is something we haven't defined yet, so I'll get there in a moment. But these are the three properties I still want to discuss with you today, and that's it. So I don't think I need the full half hour for that, but we'll see how far I get. 3 things to prove. Let's take them one at a time. If x is reducible to y and y is in P, then x must be in P. My proof for that. Okay, well, what do I know? I know 2 things. I know that y is in P, meaning there must be an algorithm that decides instances of y in polynomial time. I also have this reduction. So I have a car production that maps instances of x to instances of y. Now what do I need to do? I need to find an algorithm for x that decides x in polynomial time. Well, let me construct it. What do? Given an instance of x, I use my reduction to get an instance of y, and now I run my polynomial time algorithm that I have for y. That means that I have for y. Now, since the reduction is reliable, a yes instance remains a yes instance, and a no instance remains a no instance. And because this reduction is polynomial, what I'm doing is I take polynomial time to transform the input. Okay, the input might become a little bit bigger, right? The size of y might be x plus some amount of extra stuff. Because our reduction requires polynomial time, it could use this time to make our input bigger, but only polynomially bigger. And if I then run a polynomial on a polynomial, I get something that is also polynomial time. So by first doing the reduction of my instance, the transformation of my instance, and then calling my polynomial time algorithm, I have constructed a polynomial time algorithm to solve problems from X, meaning X must be in P. Are there questions about this? So this is the proof that P is downwards closed. I see no questions pop up yet. I'll give you a couple more seconds. So X and Y are sets of problems? Well, no, X and Y are problems. But remember, a problem is just a language, so a set of words, right? A set of instances. In our case, for instance, in Vertex cover is, in Zipser notation, is the set of all graphs, the set of all graphs integer pairs such that these graphs have a vertex cover of at most size that integer. And an instance of such a problem is a specific graph with a specific integer. Does that make sense, Meatball en Ik ben altijd wakker? Meanwhile, let me answer Harry's question. So Harry is asking, what does downwards closed mean? So you can think of it if you have this smaller than expression. Let me check in my webcam which way I should draw it for you. Yes, like this. Yeah, yes, so if x is smaller than or equal to y, this is very confusing. Okay, then it basically follows it down the chain if you want, right? If y is, yeah, y should be this one. Okay, I'll just show you on my slide. If y is in P, then this property is transferred down the chain to x. And that's what we mean with downwards closed. So if we had z is smaller than or equal to x, is smaller than or equal to y, then z would also be in P. Does that make some sense, Harry? Good. All right. All right. One last question before we move on from Fast, which came in just in time. I say that y is polynomial bound in x. Yeah, so what I mean, my reduction is going to take an instance from x, and now it's going to do some polynomial time work to transform this thing into an instance of the problem y. But what it could do, and we'll see examples of this next week, in doing this transformation, for example, from going from vertex cover to clique, maybe our transformation is going to add some nodes, or it's going to add some edges. So the input, the instance we create here, might be bigger in size than the original instance we had. But because my reduction is polynomial work, my new instance can only be polynomially bigger. And that's what I mean with y is polynomially bound in x. Right? It's everything from x, and it could have grown a little bit, but only by a polynomial amount. Good. Okay. Then, my second property that I wanted to show is that NP is downwards closed. Well, the proof is exactly the same, except that I've added the words non-deterministic twice. Right? Because now what do we have? Well, is y is in NP. So again, x to y. If y is in NP, there is a non-deterministic algorithm that decides it. Now I need to create a non-deterministic algorithm for x. So what do? Well, I take an instance, I transform it, and I run my non-deterministic algorithm. And now I have constructed a non-deterministic polynomial time algorithm for x. So NP is also downwards closed by exactly the same argument, only talking about non-deterministic time instead of deterministic time. Does that make sense, or are there questions about that? Before we move on to the last property I want to talk about. So this is a very good question, right? Which Quirky is asking us. So Quirky is asking if y is in NP, or even NP minus P, so one of these somewhat harder problems. I've been confusing x and y all the time now. This should be y? Yes, this should be y because it's on the right side of your screen. Yes. So if x is reducible to y and y is in NP minus P, so one of these harder problems, right, that we don't have a polynomial time solution for, at least not yet. Is it possible that x is in P? Yeah, for sure. Because remember, P is a subset of NP. So this reduction would show us that this problem is also in NP, but it could be in the part that is also in P. So if y is in NP minus P, then x could still be just in P. Yeah, maybe I should just point at my slides, but I'm not used to using a mouse to do so. I'll try for next time, Jonathan. Thanks for the tip. One last question before we move on from Matei. Can you explain again which way the arrow is supposed to be? So if we have an algorithm for TSP and an algorithm for a harder problem, which can be solved with TSP, would it be TSP reducible to harder TSP or the other way around? Okay, so we have a problem that we can solve by using an algorithm for TSP. Then that means that our new problem is no harder than TSP, because we can solve this problem by using an algorithm for TSP. So x reducible to y means x can be solved using an algorithm for y and some polynomial overhead. TSP, Ikdekker, is indeed the traveling salesman problem. It is a problem that we believe to be in NP minus P. But you could have replaced with everything I just said with any problem at all, right? So if we have an algorithm for a problem y, and we have a reduction from x to y, we can solve x using this problem, or this algorithm for problem y. And that seems to have answered the question. Good. Then there was one last property of car productions I wanted to discuss today, and it was about NP hard problems. So let's talk a little bit about that. We've now talked about the class P and the class NP, but also about NP minus P, and that becomes all a bit muddled and confusing. So let's see if we can make that a little bit clearer. We have P, which are easy problems. And now we said, well, NP also contains harder problems. So is there then a distinction, right? Is it just easy in P and the rest is hard? The rest that's in NP, so NP minus P, all of that? Or perhaps there is more distinction than that? Well, we can make more distinctions than that. So we have problems that we call NP complete. And to introduce that, I need to first introduce NP hard. What is NP hard? A problem is NP hard if and only if all problems in NP are reducible to it. And this is where I will once again be using my tablet to draw you a little visual. Tablet. Let's get rid of chat and Chrome on that screen so that I can show. I also see my slide contains an error, so let me start by fixing that on the tablet. Okay, hang on. Here we go. Let me show you the tablet. So thanks for pointing it out, Matei. The first X should indeed be an A. Yes, thank you, Quirky, and thank you, 61. So the definition for NP hard is this. X is NP hard. Sorry, let me use the same names now as on the slides as much as possible. A is NP hard. If and only if, for all x in NP, x is reducible to A. We can visualize this. Imagine I have some problems, and I have a set of problems that we call P. Well, P was a subset of NP. And now I'm going to draw reductions as arrows. So let's say this problem is reducible to this one is maybe reducible to this one. These are both reducible to this. Now there is a class of NP hard problems such that every possible problem in NP, and therefore also in P, is reducible to them. Right, and this one might also be NP hard. There we go. Now there is an interesting intersection, and that is the following intersection. Right, the problem with these points is that they might be outside of NP, but now consider a problem that is in NP, but also NP hard, meaning any problem in NP is reducible to it. That class of problems, and let me just draw a clean diagram to show you more clearly. Is the set of problems we call NP complete. And NP complete, anything in there is also in NP, but it's also NP hard, meaning anything in here can be reduced to problems in NP complete. Now, why is that relevant? Well, that's the question I'm also going to give you as homework to think about a little bit more formally. But let me give you some hint about it already. Why is this an important class of problems? Well, imagine that this problem, that everything is reducible to, turns out to be an easy problem. What would that mean for all the other problems in this class? It would make them easy as well. Someone asked, Lightning, if A and B are both in NP complete, does that mean that A is reducible to B and B is reducible to A? Yes, because being in NP complete means being in NP, and being in NP complete means that everything in NP is reducible to you, because you're NP hard. So yes, these two together means that anything in NPC can be reduced to each other. All right, let me hide the tablet again. Well, I think it's fine if it stays visible for a little bit. So that gives me the one last thing I wanted to show you. The last property of car productions, which has the wrong title in the books. Okay. These slides were a bit of a rush job, I'm afraid. If x is reducible to y, I was going to use the slide. If x is reducible to y, and y in x is NP hard, then y is also NP hard. So this is going the other way around, right? We know something about x, now we can derive something about y. Well, what do we know? If x is reducible to y, there must be some car production of x to y. Now take an arbitrary problem from NP. To show that y is NP hard, I need to show that this arbitrary problem in NP can be reduced to y. What do? Well, since x is NP hard, there must be a reduction from z to x. So I can construct my reduction from z to y by first doing my reduction from z to x, and then doing my reduction from x to y. and then I have constructed a polynomial time reduction from z to y, meaning that y must also be NP hard, because z was arbitrarily chosen. So this reduction we can use to show new problems to be NP hard by finding a reduction from an NP hard problem to our new problem. But like I said, if we find a problem in NP complete that is also in P, meaning it is efficiently solvable, what does that mean? Well, it indeed means, and I'd like you to try and think of a bit more formal of an answer to this. But intuitively, you might say, okay, well, if all of these problems are no harder than these problems, because they are reducible to it, then if this problem has a polynomial time solution, that means that all of these problems must have a polynomial time solution. So as some people are asking, right, a scanner is asking, if we find an easy solution to an NP-complete problem, can we solve any problem in the universe? Well, no, that we cannot. Remember, the halting problem, no matter what happens, has no solution. But any problem in NP would be easily solvable. Someone else asks, if we are to solve an NP-complete problem, can we just solve every NP problem? Well, yes. Well, remember, we can already solve them, but we could solve them in polynomial time. Yes. If NP-hard problems are not in NPC, does that mean they are exponential? Not necessarily. It is possible to create carp reductions from problems in NPC to, for example, the halting problem. And the halting problem is not even in exponential, it's undecidable altogether. Blah blah is asking, what is the difference between NP-hard and NP-complete? So NP-hard has the requirement that anything in NP is reducible to it. NP-complete puts an extra requirement on that, namely it needs the problem to also be in NP. So to be NP-complete, you need to be NP-hard, but also in NP, which is not a requirement for NP-hard. How would I show problems in NP-hard in the right diagram? Asks Fast. So they would be outside of this circle. Jonathan, how do we even prove that a problem is NP-hard? We can of course show that an NP-hard problem is reducible to it, but we need a first NP-hard problem. How did we find the first one? Very good question, and it's going to be the very first question we answer next week. So yes, indeed, NP, let me write that down here. NPC is exactly the overlap between NP and NP-hard. Yes, thank you, 61. Are there any more questions now? Let me also check whether you have any feedback fruits. Is there going to be videos for the rest of the weeks? If you mean, are these lectures recorded, then yes. If you mean, are there videos to watch? Probably not, no. So no preparation for next week's lecture. Let me get chat back up, see if you have any more questions. Wouldn't finding a problem in NPC that is also in P mean that everything is essentially reducible to P and therefore proving P equals NP? Yes, Alex, well done. And we'll be discussing that in more detail next week. If we can reduce a problem from NP to a problem outside of NP, shouldn't that problem also be in NP? No. So remember that reductions are downwards closed, right? So if I have X is reducible to, for example, vertex cover that we saw today, then X must also be in NP. But if I have it the other way around, so if, for example, I show that vertex cover is reducible to, let's say, the halting problem, This doesn't tell us anything new about the halting problem. NP is downwards closed, but not the other way around. All right. With that, I'm going to wrap up for today. So, we talked in the course already about regular languages, context-free languages. Poker ad coming up again. There we go. Undecidable and decidable languages. Now, today we talked a little bit about the hardest decidable problems. Well, not yet the hardest, but at least we saw that there are polynomial and exponential problems. We talked about the complexity of problems, and we talked about 3 classes of complexity, P, NP, and NP complete. Next week, we're going to take a closer look at car productions. I'm going to show you some examples that transform one problem into the other. Now, for this course, you will not be asked to come up with car productions all by yourself. This is something that requires more than 2 weeks of practice. But given a car production and given a proof for its correctness, you should be able to criticize that proof. So you will definitely see some reductions, you will criticize their proofs, you will apply these reductions, but you will not be able to come up with them yourself. Next week in the lecture, though, we are going to create some together. Yes, 61 is pointing out in chat as well. So does that answer your question, Pavon? Can I give examples of exam questions about complexity theory of this course? Yes, I can, and I already have. You can find them in the homework for week 6 and 7. You're very welcome, Pavon. About Rice's theorem. Yes, I should still make those slides available. Thanks for reminding me, Wakker. I'm not sure if I can get to it today, but I'll do so as soon as possible. So I've made a note. Thanks. All right. If there's nothing else, then I'm going to leave it here for today. I will see you again next week. And as soon as we know something about the exams, we will let you know. I'll stick around in chat for a couple more minutes if you have questions there. See you around.